Hi everyone, welcome back to the workshop, and it's part 3 of the HP 3458A 8.5 digit multimeter repair. Now in the first two videos I did quite a lot of the mechanical fixes, got the meter straightened out, and I didn't actually tackle much in the way of the electronics. I did fix a fuse on the AC board, hoping that would bring the meter back to life, but it just changed the error codes that I was getting on the display and presented me with a new bunch of error codes that I then decided to leave off for a third video. Well, I've done a lot of investigation, a lot of measuring, a lot of probing the PCBs inside this 3458A, and I've learnt quite a bit along the way, because although I've had 3458As in the past, they were always working, and I just did the basics of FRAM upgrades and stuff like that. Now I've already done the work to get this meter up and running. We'll talk about that because not all is what it seems, but it's been great fun and I wanted to share exactly what I've been through the past few days getting it to where I am now. Now, apologies for it being upside down again, it's just the easiest way to work on this underside of the unit. But let me power it up. I've got it in its faulty state so I can show you my starting point. So if I just power it on, you can see I immediately get an error there. And if we take a look at that error, we've got 202 hardware failure, slave test, convergence. And that's kind of a generic error. It doesn't specifically point to a particular IC in a particular board. As such, it can be a number of different things. But anyway, if we just clear it, you can see I've got no error anymore. But you'll notice I've got nothing on the display apart from the units. The actual data, the numerical data for voltages or whatever, is not appearing. But I can kickstart that. And I can do that by rearming the unit. So there's a command, tarm auto. And if I just enter that, you'll see that it is actually working. And as I showed in my first video, I think, it is actually accurate in DCV mode, in ACV mode, etc. But as I mentioned in the previous videos, not is all what it seems here, because it looks like it's okay, but if I change the NPLC to 0.1, that display there should be rocket fast. There should be a lot of samples being displayed every second. As you can see, it's about 1 per second, and there's nothing you can do to speed that up. NPLC, number of readings, and no amount of prodding around the menus was I able to help speed that up until I stumbled on one particular command. That's the timer command. So if we just go to T for timer, scroll down, timer, and I'll set that to 0. Okay, there it is, rocket fast. I'll just slow that down. MPLC 1, that's a bit slower. MPLC 10, there we go. Now the issue is, when you power up the 3458A, everything should be scrubbed. All the settings you'd made on the front panel should be scrubbed. So I couldn't work out why every time I powered it up, I had to go and put back in that timer 0 command. If I turn it off now and turn it on again, it'll be slow. I'd need to do that timer 0 again. So then I stumbled on the subroutines that you can store in the 3458A, specifically sub 0. And that is a bunch of commands that are stored in subroutine 0 that are loaded on power up. And there is a way to delete those subroutines. I did that and it still didn't make any difference. It was still slow and I still needed to use timer 0 in order to speed it up again. So I started looking at the AC board, scoping a lot of the electronics there, and I really couldn't find anything that wasn't working. And the reason I thought there was something wrong with the AC board was down to the fact if you run an autocal on the DCV mode, on the ohms mode, it's fine, it passes. And that was kind of telling me that the analog to digital converter was okay. It was a problem with the ACV mode, because when you ran autocal ACV, that's when I was getting an error. And it was throwing up a ratio error. And I chased around that AC board for a good couple of days until I decided to look elsewhere on the meter. So I moved to the A3 board here and the U180 circuitry. And what I found was, let me bring up the schematic, and here is part of the A3 board schematic. You've got the U180 current steering hybrid IC down here. That's the infamous one. It's got some embedded resistors inside it that change value or can change value over the years, and that causes all sorts of problems because there's no way of fixing it. And up the top here you've got 3 op amps, and they produce some reference voltages. You've got a plus 12, a minus 12, and over here you've got a plus 5 as well. Now the absolute value of those reference voltages is not too important, but the plus 12 and the minus 12 need to mirror almost exactly down to just a few millivolt. And what I was finding was the minus 12 volt rail had a 20 millivolt mismatch from the positive 12 volt rail. So I thought I would try and see if I could make it match up. Now there's nothing I can do with the resistors here that are part of the feedback on those op amps there. There's nothing I can do with them, but I thought maybe I'll try and bias the minus 12 volt one and try and bring it down slightly so that it does match the positive 12 volt one. So I played around with resistors across the op amp there. So nothing was really working, and I thought, well, let me try and bias pin 3. And after tracing the circuit back from pin 3, I discovered that the ZR low reference node actually ties back into the LTZ-1000, the main reference chip on this 3458A. It actually ties back into the LTZ-1000 reference low system. Because if you measure the resistance from pin 3 of that op amp, you see I've got a little green wire hanging off of it. If you measure the resistance between it and the 0 volts on the A3 board, it's about half an ohm. And I think that half an ohm is just all the wiring and the tracks going away off back to the LTZ-1000 reference that lives on another board on the other side of the meter. So my fix, in order to temporarily bias that minus 12 volts to match the positive 12 volts, was to inject a small current into pin 3 that would create a little offset all the way back to the LTZ-1000. And that would effectively shift the analog reference ground by just a few millivolts. Just enough to rebalance the positive 12 and minus 12 reference voltages. So I'll hook that up now and I'll show you what happens when you power it up. So I've got a PDV-S2 Mini there, set to 5 volts. I've got the output of it through a series 1K resistor and then onto that pin 3 of that op amp. And if I just power it up, powers up perfect, no errors, and no longer needing to do that timer 0. It's working perfectly. And I can NPLC 1 and it's rocket fast. So by injecting 5 milliamps from the PDV-S2 Mini through that ground system, it has the effect of altering the minus 12 volts VREF from that op amp, and it brings it closer in line with the positive 12 ones, so they match. And that's why when I power it up I get absolutely no errors and it's working. Now that's not a permanent fix. There's no way I could install anything like that into the system here, because it's going to have other effects elsewhere, linearity, accuracy, all sorts of things. The problem is in the U180. Let's go back to the schematic. The problem is going to be inside the U180 IC, and a mismatch between the various different resistors that are supposed to be matched within that chip. And effectively what's happening now is it's biasing off the minus 12 volt output, or it could be the plus 12 volt, because like I said earlier, it's not important the accuracy in terms of exactly 12 volts. They just have to match, and they have to be somewhere around plus or minus 12 volts. So the problem is the U180, and that is unfixable. I have to remove that chip from the board and install a new one. However, you can't get them. So some of the guys on the EEV blog forum have a replacement board that they're working on that allows you to plug it into the socket where this U180 lives, and it replicates the exact functionality of it by way of a CPLD and a bunch of other chips. And it's working pretty good at the moment. There's still a ways to go, but it's working pretty good. So my next step is probably going to be to remove that U180 from this board here and build an NU180 and get it installed. So what's required to do is remove the U180 from the board, and as if by magic, there it is removed. We'll put a socket in its place, and then we'll assemble this board here, have some pins on the bottom side so it can plug in, and then we'll try it out. Now the NU180 is still a work in progress, both on the software inside the CPLD and the hardware. There are some challenges to overcome in order to make it work as a replacement for the U180. But it's in a place right now where it is actually functional. So I thought I'd actually try it myself. So I monitored the forum posts, and Zondar actually came up with this design here. I've taken the original KiCad files, done a small modification myself regarding the precision resistors, and that's why it's called the E&J V1 variant. And I'm going to assemble this board here, and we're going to try it out. So first things first, I do actually need to paste up the board. I've got it set here, my little assembly here. I've got the stencil already, it's already lined up perfectly as you can see. And I've got my GC10 solder paste here. It hasn't been used in quite a while, but it has been kept in a sealed container in a fridge all these years. So I'm actually quite confident that it's going to be okay, but I won't know until I get inside here. So I need to put a bead of paste along the top of the stencil there, and then I'll be able to use my spreader here to wipe across the stencil and the paste down through the holes onto the circuit board. The most important thing about pasting a circuit board with a stencil is one swipe only. And what do I mean by that? I mean, well, once I've got the paste on the stencil, it's a case of one swipe across the entire board in one go. That's it. The worst thing you can do is start doing this sort of thing and trying to get all the holes in the stencil filled with paste. And the reason that's a bad idea is because if you go over it multiple times, all you're doing is squeezing paste down through the hole, out through here, and it'll spread out the sides, and basically it'll cause the paste on the pads to mix together. Instead of being individually pasted pads, you'll just get one mass of solder paste. And when you put that in your oven or on your hot plate and try to reflow the paste, you're going to end up with short circuits. The other thing that you need to do is apply quite a bit of force down on the stencil like that there. I'm actually bending it so that when you swipe across, you're actually wiping all the paste off the top side of the stencil, or most of it anyway. Well, look at that paste. It's actually quite good. I think we'll get away with that. It's not dried out at all. So I'll give it a little bit of a mix up, and then I'll put paste on the stencil. As you can see, I put a bead of paste right across the stencil, right across past both ends, the first and last pad. So now let's take my applicator here and I'll just go down behind it, quite a bit of force. And there we go. And the next thing to do is to lift up the stencil, expose the board, and lift the board out. And let's take a look at that. As you can see, all the individual pads have all got a nice layer of solder paste on it. Even these fine pitched ones down there, perfect. Now we're ready for assembly. So I've got my tweezers ready. I won't video that. I'll just go ahead and assemble all the parts onto the board, ready for the reflow. Well, that's all the components placed on the circuit board, bar one. I went and ordered the wrong IC. I ordered a 573 instead of a 574 for U10. So I'll have to place that one once it comes in. But I'm going to go ahead and reflow the board anyway in the oven. I've placed every other component. And I've left off some resistors. The 100k resistors I think are optional. So I'm leaving them off for the time being. So next step, into the reflow oven, and let's see if we can reflow the board. Okay, I haven't used this in quite a while, couple of years actually. So let's get switched on, and I'll just select the right profile for the GC10. I think that's right, and I'll put the board in. So very carefully lay it into the middle of the oven. Perfect. Shut the door and I'll start the profile. I used to use this reflow oven quite a lot when I was assembling PDVS2 minis, and I customized my own profile on it specifically for the GC10, and it turned out quite reliable. Not sure if you can see that, but there's the profile there. And you can see the thick trace following the profile. Okay, right. Should have cooled down enough by now. Let's take it across the workbench and have a look. And there we go, that's it reflowed perfectly. Apart from this IC down here, as you can see, there's absolutely no short circuits across any of the ICs whatsoever that I can see, even these fine pitch components. So it's looking good. So I'll go off now and order up the 574 and get it fitted, and then we can actually do the rest of the assembly. I've got the socket to put on here, or the headers to put on here, and the programming header also.